Okay, so for this, just listen and enjoy, and then I will bring up a few problems where you'll actually take notes. This is in your ebook. Uh, recall that this is the form of a non-homogeneous linear differential equation. So whenever I'm going over things in the book, I don't expect you to take notes on that. Usually it's just sort of conversational. Who can see the book okay? Is the ebook showing up? Okay, Matthew says to refresh the screen for Zachary. Matthew sees the screen. And okay, very good, Zachary. So, homogeneous differential equations, that's where the right hand side, the function after the equal sign is 0. Homogeneous differential equations with constant coefficients. All we need to do is identify the auxiliary equation, and then we can find the roots of the auxiliary equation, and then we can construct the solutions. But now what we're considering is, what if you have a differential equation with constant coefficients, but you have a non-zero function on the right-hand side? That's the non-homogeneous linear differential equation. How do you handle that? Well, what you have to do is you have to use a method of what's called undetermined coefficients. The method of undetermined coefficients. So how's this work? Let's look at an example here. Example 1, okay? So here they have a differential equation, a second order differential equation. It's non-homogeneous, and the right-hand side of the differential equation, well, first of all, what we have to do is we have to find the complementary solution. We're using the superposition principle for non-homogeneous differential equations. So we have to get the auxiliary equation, okay, for the homogeneous differential equation. And the auxiliary equation, let me just, there's the diffie-q, but hold on, this is the auxiliary equation right here. And based on that, by finding the roots, the complementary function of the differential equation is right here. Okay, but then what you have to do is you have to make a guess as to what a particular solution would be to this differential equation. And for that, you look at the right-hand side of the differential equation. You notice the right-hand side is equal to 2x squared minus 3x plus 6. Okay, so the differential equation, the right-hand side is 2x squared minus 3x plus 6. So a good guess for there's a squared term. That's right, an x squared term. Well, we need more than an x squared term, Matthew. We need more than that, actually. What we need to be complete is to have y of p equal ax squared plus bx plus c. Okay, that's what we have to have. So the guess that you're making for the particular solution is based on the right-hand side of the differential equation. So like hold on, let me get this off. One moment. I don't want any interruptions here from email. The right-hand side of the differential equation determines your guess. Whatever, so like I said, in this case, the right-hand side of the differential equation was, hold on, got too much, one moment. Yeah, the right-hand side was 2x squared minus 3x plus 6. So the guess for the particular solution is going to be then ax squared plus bx plus c. Okay, and I'm gonna take you on an example. We're gonna look at an example here, but let me just show you the different table. I'm going to take you through the process here. So I'm going to do another example and take you through the entire process, okay? But I want to just sort of, I hope I've whetted your appetite for this table here that I'm going to show you. This table 4.4.1. So what this table is, it gives trial particular solutions based on what g of x is on the right-hand side of your differential equation. And you had a little practice with this if you, the 4.1 exercises that were due today, the very last question you had a little practice with some very simple g of x functions. Matthew remembers that, sure. So, like for instance, if you have if g of x equals 1, if it's a constant, the form you're going to use is a for your guess. If the second line, the second row, if your guess is 5x plus 7, you're going to then use ax plus b as your guess. Line 3, if you're right, g of x is 3x squared minus 2, then your guess is going to be ax squared plus bx plus c. And it has to do with, you know, you have to make a guess that's going to help you solve the differential equation. And so the right-hand side function clues you in. Look at here at row 5. Row 5, you have the sine of 4x. Well, the sine of 4x, your guess is going to be a times cosine of 4x plus b times the sine of 4x. And the reason it's that is because, remember, you're going to be differentiating your particular solution at least twice if you have a second order differential equation. And so you're going to generate cosines and cosines. And so you need to have a very general guess. And so that's why if your g of x equals the sine of 4 of x, as in line 5 there from table 4.4.1, the guess is going to be a cosine 4x plus b sine 4x. Now, one more. Look at 8 here, at 8, row 8. So there you have a product of two functions. You have a product of 9x minus 2 and e to the 5x. So a natural guess for there would be a product of two functions, ax plus b times e to the 5x. And for row 9, you can see they do the same thing. Okay, so hopefully, this is somewhat intuitive. I mean, you're just learning it, but it's meant to be kind of intuitive. Are there any questions on that?
None for me.
All right. Very good. Well, then let us go ahead and look at a worked out example I did. Okay. All right, so we want to solve this differential equation, and let me give you a moment to copy the example down. Okay, so I see people are making guesses already here, and let's see. Zachary, you are almost correct. Zachary, you're almost correct. So what you have here on the right-hand side is you have a function plus another function. And so you have to make a guess for this function. And so the guess for that function would be indeed ax plus b. Okay. Ax plus b. And what would the guess have to be for this function here? It's a product of two functions, 6x and e to the 2x. So, well, the e to the 2x, we're almost right, Matthew. E to the 2x. And we're not going to be doing any integration here. But what about the 6x? What about the 6x? There we go. Good, good. All right, Antonio, that's right. This would be, although of course it has to be CX. And we're gonna show, I'm just sort of helping you feel comfortable. We're gonna, formally have this in our notes. It's gonna be CX plus D. Now, normally we would have a D, but I'm going to put an E, and the reason is because the book uses the letter D for what are called differential operators, and we didn't study that. But you can put a D if you want. But we have to use different values, different coefficients. Okay, being that we used A and B here, we have to use different coefficients here. C and E. Let me see. And yeah, so think of it like this. 6x is a polynomial of the first degree. So CX plus E is a polynomial of first degree. It's as general as you can be. As general as you can be. Okay. Are there any questions so far? All right. Excellent. 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 Matthew's good. And okay, well, let us proceed. So remember the solution by the superposition principle, the general solution is going to be the sum of a complementary function, y sub c, and that's the solution to the homogeneous differential equation. That would be the differential equation where this entire right side equals 0. And then you're going to add to that a particular solution. Okay? So, all right, first we're going to find the complementary solution, and then we'll find the particular solution, and then the general solution will be the sum of those two. Okay, so let's go to the solution here. Let's go ahead and start. And remember, if you click on the screen twice, it should blow up the thing for you. But okay, so all right, so this is the solution, of course. This is the solution to our example. And sorry. Don't need that there. Okay, so what's the auxiliary equation for y double prime minus 2y prime minus 3y? What's the auxiliary equation that goes with that?
The non-homogeneous version.
Right. So auxiliary equation. So now I'm going to paste myself. This you should copy down. It's going to be m squared minus 2m. I got too much going on here with this arrow. Hold on. M squared minus 2m minus 3 equals 0. So for the homogeneous differential equation, that's your auxiliary equation. Okay, that's your auxiliary equation. And that actually, is that factorable? No, Zachary, you don't need to write down the e to the mx part. All we need to do for solving a homogeneous differential equation now, since we know the theory is true, is we identify the auxiliary equation and find the roots. And so here, the roots are gonna, let me see, we got, if we factor it, it's gonna be what? What are the factors of m squared minus 2m minus 3?
M minus 3, m plus 1.
Sounds good, Antonio? M minus 3 and m plus 1. And so the complementary function is going to be C1. This is by section 4.3. We have two distinct real roots. So the complementary function is going to be C1 e to the negative x plus C2 e to the 3 of x, e to the 3x. And now we need to find the particular solution. To the non-homogeneous differential equation. So remember, this here is the non-homogeneous differential equation, and I need to find my y sub p, which is the particular solution. So what we have to do, and I'm sorry, it's a little, we're using the method of undetermined coefficients. This is what this method that we're doing is called. It's called, I'm underlining it here, the method of undetermined coefficients. So we're going to use the method of undetermined coefficients to make an educated guess for our particular solution. Okay, so we're using the method of undetermined coefficients to make an educated guess for our particular solution. And this is going to be our educated guess. Y of p is equal to the sum of these two particular solutions that correspond. The right-hand side of the differential equation, here consists of the sum of two functions. So we identify the particular solution that goes with the form of the particular solution that goes with 4x minus 5. And then we do the form of the particular solution that goes with 6x times e to the 2x. And this is what you get. I made an error in my work, so I had to do quite a bit of erasing, but I think I got it erased pretty well, you know. Okay, so now what I'm going to do now is I'm going to write out my particular solution, and I have to substitute it in the non-homogeneous differential equation and solve for A, B, C, and E. That's what I have to do. That's why this is called the method of undetermined coefficients, because A, B, C, and E, I have to find out what those are. Okay, so I'm going to have to take two derivatives of the particular solution. And I have to use my derivative rules very carefully because the product rule is involved and the chain rule is involved. But A, B, C, and E are constants. Okay, so I think it's pretty clear the derivatives, how I did them. I mean, let me know if you have any questions on how I got the derivatives. Let me know if you have any questions. Okay, good, Matthew, good, good. I definitely want to be clear. Okay, so, and again, table 4.4.1 in the book is the reference table. But, you know, once you get enough practice with this, you're going to, you're probably not going to need to refer to that table. It's going to be intuitive. Okay, who needs a little more time to copy? All right, Matthew's good. Zachary, this is table 4.4.1. It comes from section 4.4. It's that table in the book that I showed in the a little earlier from the ebook. Table 4.4.1 in the ebook comes. Hold on, it comes right after example 4. Okay, in the ebook. All right, so now that we have the derivatives, let's go ahead and move forward. We have to substitute in both of our derivatives for our particular solution and our particular solution itself. We have to substitute them into the differential equation in hopes of solving for A, B, C, and E. And so here, okay, we're requiring that when I substitute in the particular solution into the differential equation, that the result is going to be it equals 4x minus 5 plus 6x times e to the 2x. So this works a little bit like partial fractions. You have to group things, but let me give you a moment just to copy things down, okay, and then we'll you know, we'll talk. Okay, so you can see that, you know, here was the second derivative for our particular solution, minus 2 times the first derivative of our particular solution, minus 3 times the particular solution itself. And what I do is I try to kind of separate things out. So there are terms here that have a common factor of x times e to the 2x. So if I bring those terms together and factor out the x times e to the 2x, I'll get 4c minus 4c minus 3c. For the terms that have an e to the 2x, there are 5 terms. If you look up in here, there are, for instance, 5 terms that have e to the 2x power. Let me see. Here, maybe I can put it in. Hold on. Okay, there's this term here. This term times -2. This term times -2. And then this term times -3. And so you see, if you bring those all together and factor out e to the 2x, this is going to be the what comes in front. And you know, some nice things happen. You get some cancellation. Usually, if you're doing things right, some terms will cancel. And then I get it down to, you know, I reduce it even further. And this here, this expression has to equal then 4x minus 5 plus 6x e to the 2x. So this is like the left side of the differential equation. This is the right side of the differential equation here, and they have to be equal if that particular solution is a solution. And we make use of that fact then so that we can you know, solve now for these coefficients. So it's a little bit like partial fractions. You equate like terms together. I want to say it's the right way. The negative, well, okay, so the negative 3ax, and this is all in the recording, of course. The negative 3ax has to be equivalent then to 4x. So that means negative 3a has to equal 4. We have 4 variables. We need 4 equations. The negative 2a minus 3b, okay, that has to then, that's a constant. There's no x variable there, so that has to equal negative 5. So that gets you this equation. All right, and then the, let me see here. The negative 3c x times e to the 2x, okay, well, that has to equal 6x e to the 2x, and so negative 3c equals 6. Okay, and then finally, the 2c plus 3e times e to the 2x. Well, there's no e to the 2x term here. I mean, we can think of it here as plus 0 times e to the 2x. And so, you know, 2c minus, this is a minus, sorry. 2c minus 3 equals 0. This is a minus here, right here. That's a minus.
Wait, where did you draw the minus?
Right here.
Oh.
Right there. I looked like a plus, you know, kind of debatable, and I'm sorry about that. It's a minus. It's a minus. Okay. What happened was I took I had the notes, I copied them a little bit darker so things would show up. And it kind of unfortunately brought in some of the eraser things too. But we're okay. We're okay. I'm clarifying everything. So now you have here 4 equations. Very good, Matthew. 4 equations and 4 unknowns. And of course, we could solve the equations by hand, no problem. I mean, certainly by the first equation here, we know that A would equal -4/3, and by the third equation, C equals -2. And you can solve for the other 2 variables. You'll get B equals 23/9. B equals 23/9. Okay, this is just, yeah. B equals 23/9, and then E equals -4/3. But there's a MATLAB program I'll share with you that also shows how to solve how to solve this system of equations. I mean, it's okay if you want to use my MATLAB program, and I'll show it to you to solve that system of equations. So this procedure, I mean, we now basically have the particular solution. We know what the particular solution is because we know now what all of our coefficients equal. We know the values. So we know what y sub p is, the particular solution. All right? Are there any questions?
None for me.
Okay. May I move to the next page? Is anybody still copying, or are we good? Maybe a few thumbs up if you're ready. Okay, Matthew's good. Christopher's good. Okay, then let's move forward here. So, okay, here's the particular solution. Here it is. And so the general solution to the non-homogeneous differential equation is equal to the complementary solution plus the particular solution. And that's what you would type in WebAssign. Now, this is a general solution, right? We have not been given any initial conditions. So we have general coefficients C1 and C2. But of course, if you were given initial conditions, and I know there was a question, I'll get to it in 1 minute. If you wanted to solve for C1 and C2, how many initial conditions would you need?
2.
You would need 2. You would need, that's right. Justin, and that's right, Zachary. You would need that, for instance, y of 0 equals a value, and you would need to know y prime of 0 equals some value. You would need two initial conditions. Okay, so there are going to be problems where you do have initial conditions, and you know how to handle that kind of problem. This is sort of the key thing, getting here. So you can see this process is very dependent on identifying the correct particular solution and doing your derivatives properly, not making an error. Okay, because if there's an error in your derivative, even just one error, it's going to you're going to get the wrong answer. Okay, so I want to show you a program I wrote that I think will be helpful for you for these problems from section 4.4. All right, so let me go there. If we're good here, if you go into your Blackboard, are there any questions? All right, if you go into your Blackboard here, and I'll bring it up. Let me see here, sorry. Hold on. Okay, wait. One moment, class. Make this right here. Okay, so we're in here, right. Go to MATLAB Programs, click here, and there's a MATLAB program for section 4.4. And a program will help you check derivatives and solve a system of linear equations. Okay, so you just click on the program, and it will, that link, and it will download the program. All right, so take a moment to do that. And I'll show you the program here. Okay, let me get the, hold on here. There was, okay, good. Matthew's found the program. Let me see here. I got to just find it in, hold on, I'll have to bring up my MATLAB. Sorry, I hit the wrong button. One moment here. I'm back. Let me just get the thing. What I'm doing is I'm going into MATLAB and getting the program, but I got to click on the program to get it. And There we go. Got it. Okay, can everybody see the MATLAB program okay on the screen? Okay, thank you, Andrea. Maybe give me a thumbs up if you can see the program all right. Couple thumbs ups. Okay, excellent. Thank you, Andre. Thank you, Max. So what I do, I always start off with clear vars. Thank you, Andrea. Clear vars, clear variables. I don't want any old variables interfering with what I'm doing. So I wrote here the particular solution. I wrote it. And I wanted to check my derivatives. So I have the diff command. Take the derivative of the particular solution with respect to x. And then for the second derivative, take the derivative of the first derivative with respect to x. Okay? So that will, if you copy that part, okay, and paste it on the command line, and it takes a moment, but it'll confirm your derivatives for you. Okay, so how many think that's kind of cool? Kind of nice. Okay, good. Andrea likes it. Thomas likes it, and it's good. And you know, you can get the derivatives can get, they can get interesting. So it's good to check your derivatives. And now the other part of the problem was solving those linear equations. So to do that, let me do a CLC here for clear screen. So this is the command to solve those equations, and I use the command format RAT so I get fractions, because WebAssign, when you can get exact answers, it wants them, and that means fractions. Okay, so it'll tell you if it wants you to round to the nearest decimal or something. Put it in, and there are your coefficients. Okay, are there any questions on that? Okay, so I want to continue. I want to do another example with you. I want to do another example here. Okay, now this is just a little bit of practice on identifying the correct form of a complementary function. All right, Christopher, it'll be on the recording. Thank you for letting me know. We want to identify the correct form of a complementary function and then a particular solution. Thank you. You too, Chris. Thank you. And then a particular solution for each differential equation below. Okay, so take a moment to copy this down. The reason I'm doing this is we did a problem where we worked out a problem. But of course, you have to get good at identifying the correct, the complementary functions. You got to be able to get those, but also identifying the correct particular solution. Okay, so all right, take a few moments here, and then we'll go over this. Take a few moments to copy, and let me know if you have any questions. Okay. Okay, and while you're copying, I'll just make a comment. So I know that, I originally was going to have, So I have 3 classes, and and the other classes, their remedial problems end at, like, at whatever time the class meets during the day. So I really don't need to be consistent, but I try to do my best. I try to do my best. I really do, in terms of giving you the time. But I give 4 days for those remedial problems, and I try to do my best. But all right, see me after class if you have any questions. All right, let me let you copy here. Okay, who needs a little more time to copy?
I'm done.
All right, very good. Okay, so here's the first differential equation. What equation do we use to find the complementary function? Y sub c, what's that equation called? Begins with an A.
Auxiliary equation.
Let's see,
Auxiliary.
auxiliary equation. Good, good. So what would the auxiliary equation be for the first differential equation? And the auxiliary equation, all you need to do is look at the left side.
It's just equals 0.
So the auxiliary equation will be something equals 0, but it's going to be, that's right, Zachary, m squared minus 2m plus 5. M squared minus 2m plus 5. It corresponds to the derivatives, the coefficients of the derivatives. So if I go to the next page here, m squared minus 2m plus 5, it can be easily shown that the roots to that equation are 1 plus or minus 2i. And I wrote the differential equation down just to for reference. So based on what you learned in section 4.3, your complementary function is going to be c1 times e to the 1x power cosine of 2x. Notice you got a 1, that's your alpha, and a 2, that's your beta. So the complementary function is c1 times e to the 1x cosine 2x plus c2 e to the 1x sine of 2x. Now the right-hand side of the differential equation, the right-hand side is e to the x times cosine of 2x. So the particular solution we would think would be e to the x times a cosine 2x plus b sine 2 of x. But look at what we have. Look at what we have here. I've inserted an x here. Why?
To make it not to be dependent on the complementary function.
That's right, Michael. That's right. That's right. So what happened was in the complementary function here, you have e to the x cosine of 2x and e to the x sine of 2x. Well, when you get your particular solution, if you distribute the e to the x to, both of these trig functions, you're going to get these back. You're going to get e to the x sine of 2x back, those functions back. And so you got repeats. And so because of the repeats, you need to introduce an x. Now, of course, that's going to make taking derivatives harder, but we have to deal with it. And we do have a program that can help us check our derivatives. So then the particular solution, this is going to be what the particular solution looks like right here. Okay, are there any questions on that? If you don't have the x there, if you don't have this x here, it won't work out. You'll get in example 4, they show you what would happen if you did not have it's for a different problem, but it'll show you what will happen. You just won't be able to solve for your coefficients. And it has to do, as Michael was saying, about linear independence of the functions that the little functions that altogether compose your general solution. Okay, the next one is m cubed minus 6m squared equals 0. I'm sorry. The next differential equation was y. The third derivative of y minus the second 6 times the second derivative of y equals 3 minus cosine of x. Okay, and using the MATLAB program, you wouldn't need it really for this, but well, your auxiliary equation is m cubed minus 6m squared equals 0, and your 3 roots are here. And so now you get your complementary solution. But look at what you have here. You have a repeated root. So in the complementary solution, you have c1 times e to the 0x. I want to be careful here. Yeah, you have a repeated root. So you have c1 times e to the 0x power plus c2 times e to the 0x power times x. Because the arrow means, because it means it's for a repeating value. And then you have c3 times e to the 6x. There's no x here because that's not a repeat. And so the complementary solution, y sub c, is going to equal this here. Okay. Are there any questions so far? All right. Well, now on this g of x on the right-hand side consists of the difference of two functions. So the cosine of x, that's easy enough. We should use b cosine of x plus c sine of x for that. But the 3, normally the 3, we would just have an a. But we can't just have an a because we have a constant here. hold on here, let me, okay, we have in the complementary solution, we have a constant right there. So we can't just have a constant A here for the 3. Okay, so you might say, well, let me put an AX, A times X. Well, we can't stop there because we have a C2 times X here in the complementary function. So that means we have to have A times X squared. You see that? See how that works? Let me know if you have any questions. Okay, then if we're good, I'll go to the next page.
Wait, so it's just because like they have it's another. It can't be the same, right?
That's correct. That's correct. It can't be the same. So since you have a C1 here, like normally for the 3 in your particular solution, you would just put an A there, right? But you have to have linear, and this will answer your question, Zachary, too. You have to have linear independence between all your terms. So the fact is, if you put just an A here, you have a constant here. You have the C1 constant there. So you can't just have a constant here. You have to distinguish it from that other constant. Okay, so you would say, okay, A times X, but you have a C2 times X here. You have to distinguish this part from that. So you have AX squared. All right, does that help a little bit? All right, let's keep going. Let's keep going. Let's go to C here now. For C, this was the differential equation. Okay, and the auxiliary equation gives us 2 distinct real roots. So your complementary solution is it's simply this. And then your particular solution is going to be the difference of, well, you got to write a general particular solution that takes into account the difference of those 2 functions on your g of x here. So for 16, I'm going to put the constant a. And I can just put a. I don't have to put a times x because there's no constant in here. You know, there's no like constant sitting there in the complementary solution. So a is like independent. Okay. But now look what happened here. Look what, hold on here now. I think I have a slight error here. One moment. Hold on, one moment. Yeah, this should be a 4 here. I mean, it was right in what you copied down. It was right. But in this here should be a 4. Okay. That should be a 4 there. So, all right. So far so good. But now look what happens. You have here an e to the 4x, but you have an e to the 4x here. Okay, and so normally what you would do for this function here, you would write bx plus c times e to the 4x. But the problem is when you multiply e to the 4x, when you distribute it to the bx plus c, you're going to have a constant times e to the 4x. You're going to have a term like this, a repeat. So you have to put in an x to account for that. You see how this works? And I have just one more to do, If you can stay a few extra minutes, I'd appreciate it. If you have to go, I understand, but we're almost done here. Are there any questions? Okay, final one. Y double prime plus y equals 2 times x times the sine of x. So the complementary, the auxiliary equation is m squared plus 1, okay, equals 0. And we solve. M is going to be plus or minus I. So, you know, when you have I is equal to 0, you know, plus or minus 1 times I. You can write it that way. And so based on that, this is where that 0 comes. So your complementary function is C1 cosine of x plus C2 sine of x. But again, be on the alert. You have a sine of x here on the right-hand side in your g of x function. So normally you would for the right-hand side here, this is all in the recording. Normally for the right-hand side, 2x times the sine of x, okay, you would just have c cosine of x plus e sine of x times ax plus b. But again, that sine of x, when you multiply that all out, you're going to get repeats that look like a constant times the cosine x and a constant times the sine of x if you FOIL this out. And so you have to introduce an x right here. And then if you like to work at the math out, I don't want to have to worry about, well, I mean, you know, if you just kind of work it out, you can write it, your final particular solution in this form. Okay, you can write it in that form. Okay, and I think that I'm just trying, I showed it out here. Are there any questions? Any questions at all? Okay, Matthew's thinking a little bit.
I guess why did you put these you just created these all these different new coefficients that represented two coefficients?
Yeah, because I didn't want to have so of course I'm distributing here c cosine of x to
Yeah, I
the
saw that.
ax and to the b. And I don't want to have a coefficient called AC and BC. So I'll just call them F and G. That's all. That's all I'm doing. And similarly here too, you know, E times the sine of x times AX, E times the sine of XB. Yeah. Okay, very good. Any other questions? Very good question, Matthew. Okay, let me stop the recording.